the statement, 1, and then everything falls apart. But to prove something is true, you have to show that it's true for all values, all possibilities. That's a lot harder. Okay, so the next thing we're going to do is we're going to do the assumption. So the assumption, I like to do it this way. There's a few other ways of doing it, but I like to do it this way. Oh, see, this thing was broken last semester. They had all summer to fix it. Not working. Okay. So I can't use the upper board, which would be nice because it's more board. So the assumption basically will be, we will have J will be our variable. Since we already covered the case where n is equal to 1, we can let J be greater than 1 because 1 is already true. So we will assume that it's true when J is greater than 1, but less than n. What's n? N is some hypothetical large number. It can be anything, it can be as high as you want, so there's no limit on it. So if we assume that it's true for J, we will assume that the summation as I goes from 0 to, what's the assumption going to be? We'll replace 0 to J minus 1, J minus 1 of 2 to the I will equal to 2 to the J minus 1. So all we really do is replace n with J. The assumption is not complicated. What's complicated is now going to the final step, which is the proof step. So now, so that's the assumption. Notice the assumption starts with 2 and ends with n minus 1. So the largest discrete value on the upper bound is n minus 1. And since we're assuming it's true, we go to the proof step, and in the proof step, we want to show that this is true. We want to show that this is true. To show that this is true, we will grab the assumption and we'll maximize the assumption. So we'll plug in, I'll just write it here, plug in n minus 1 for J. Why? Because the assumption says assume from 1 to less than n. So therefore, when we do that, we go into the assumption and then we go I is equal to 0, we plug in n minus 1 for J. So it's going to be n minus 1 is n minus 2 of 2 to the I is equal to, now plug in here again, plugging in n minus 1 for J is equal to 2 to the power n minus 1 minus 1. So this is the maximized assumption. So this is the assumption. In the assumption step, in the proof step, we maximize the assumption. Now we have to think. Thinking is very important. So we're going to think and we're going to say, how do I finish this? Well, I need to show this. So therefore, what I'm going to do is I'm going to try to find out what is the sum from 0 to n minus 1. So the sum as I goes from 0 to n minus 1 of 2 to the I is equal to, and what I'm going to do is basically, notice that the assumption gives me the sum from 0 to n minus 2, which is 0 to n minus 2, which is only 1 short of what I have. So therefore, I am missing which term? I'm missing from, this is from the proof. I'm missing what? I'm missing the value when I goes to n minus 1. When I goes to n minus 1, this is equal to 2 to the n minus 1. Plus the summation as I goes from 0 to n minus 2 of 2 to the I. Keep in mind that this is nothing more than the summation as I goes from n minus 1 to n minus 1 of 2 to the I. So that's a single term. Single term, but that's only one term. That's I only goes to n minus 1. Therefore, this is 2 to the n minus 1. So this is that missing term from the top, and this is the assumption, everything but that missing term. Okay? I'm going to erase that bottom thing, just so I can use more space here. So, does everybody understand how I got these two pieces? Okay, so now what I'm going to do is I'm going to say, repeat this first one, and then I'm going to add to it, and the assumption says that from 0 to n minus 2, when the assumption is maximized, I get 2 to the n minus 1 minus 1. So this is going to be plus, I'm going to add to it 2 to the n minus 1 minus 1. So this is the last element in the summation, and this is elements 1 through, or 0 through n minus 1, and this is the nth one. So now all I need to do is I need to add them together. So when I add them together, I notice that this element and this element are the same. So it's this plus another one of these things. When you add two of the same things together, it's the same thing as multiplying them by 2. So 2 to the n plus 1 plus 2 to the n plus 1 is 2 times 2 to the n plus 1, minus 1 rather. And then we have minus 1. So I simply write these two as double of the term. But that means that if I do that, then 2 times this is nothing more than 2 to the power of 1 times 2 to the power of minus 1. And when we have the same basis to different powers, what do? We add the exponents. So when we add these exponents, we get 2 to the power of n minus 1. And you can see that the left side matches what we're trying to prove, and the right side matches the value we're trying to prove it to. So when we do this, this step completes the proof, because we're showing that the sum from 0 to n minus 1 of 2 to the I is equal to 2 to the n minus 1. So for example, if I have the summation as I goes from 0, let's say 0 to 11 of 2 to the I, that's a lot of additions. That's 1, 2, 4, 8, 16, etc., etc., etc. That should be equal to, so what's the value of n minus 1? N minus 1 is equal to 11. So n is equal to? N is equal to 12. N is equal to 12. So therefore this will equal to 2 to the 12 minus 1. And now we can be certain that this is correct, because we proved it. So what's 2 to the 12? Well, I don't know, but 2 to the 12th is 2 to the 10th times 2 squared minus 1, and that's going to be 1,024 times 4 minus 1, so it's going to be 4,096 minus 1, so it would be 4,095. So we can apply it once we prove it. Okay. All right, so I think this is a good time to stop. Yeah, it's got to stop right here. Okay, I'm going to stop here. I will give you guys an assignment on Friday. And the assignment will be basically proof, direct proof, indirect proof, and contradiction. We end up contradiction. I don't have time to do contradiction, but don't worry about it, because your assignment is not due until next Wednesday, so I'll totally cover it in class, and you'll have a chance to do it. So we'll do a few of the proofs more on Monday. If you have any questions after that, you can ask me questions. You can ask our lovely GA who's back there questions. He's going to be on Canvas, so please feel free to communicate on Canvas. You can message him, you can message me, you can message each other. There's discussion forums, please use those. Okay, I'd like to see that. If you're having a problem with something, hey, does anybody know how to answer this question, or what's the best idea to follow here? Try to, not get answers from somebody, but helpful hints so you can be pushed in the right direction. Okay? So, that's it. Any questions?
Is there a textbook that goes with this?
No, there are going to be notes. The notes that I'm showing you are there, and also, once Canvas goes live, you will have access to the MIT book,
Okay.
which has some good stuff in the appendix for this. Not in the chapters, but in the appendix. So what I'm doing right now is I'm doing sort of a underlying, all the things we're gonna be doing for the semester, I'm doing them right now. So it's but it should be a little bit of proofs, a little bit of algorithms, a little bit of complexity, and, what else do we do? And then mathematical foundations. We're gonna do mathematical foundations, and from then on, we're gonna start applying those things in our work. Okay.